Next, we will look at a different scenario. Here we are not assigning a value of this numerical expression to a variable. However, an overflow occurs even though we are not storing the result in a variable. So what this line is doing is it's computing an average. Here we are computing an average of two integers. So by default, the type is assigned int. So notice the number is here 2 billion. So we are adding 2 billion plus 2 billion, result is 4 billion, then dividing it by 2 again. So the result should be 2 billion. Let's see what happens when we continue the program. Notice now the average is a negative number, which means an overflow occurred. And the reason why this happened was because the data type of the result of this expression is the type of the largest operand. So the two operands for addition is signed int. So both of them are signed int. So even the result will be a signed int. So signed int can hold 2 billion. 2 billion is less than 2 to the power of 31 minus 1. But a signed int cannot hold 4 billion. 4 billion is greater than 2 to the power of 31 minus 1. And therefore, an overflow occurred when this addition was performed. So before even the number was divided, an overflow occurred, and the division happened only on the overflow. Now we will see how to fix this soon, but let's see a different variant of the same problem, wherein we are adding 2 billion with 2 billion, so the result is 4 billion. And this time we are saving it in a long. We've seen before that long can hold 8 bytes or 64 bits. So 4 billion should be a number which is less than 2 to the power of 63 minus 1, which means there should be no overflow in this case. So let's see what happens when we print this variable my money. Okay, my money is still negative, which means an overflow occurred. And the reason this is the same as before. On the right hand side, we have a numerical expression. The result of this numerical expression will have a type which is the type of the largest of its operand. The operands are of both signed int, so the result will also be a signed int. And a signed int again cannot hold 4 billion. The maximum value of signed int can hold is 2 to the power of 31 minus 1. So what happens here is that the result is then implicitly converted into a long and then stored in the variable my_money. So a conversion from a signed int to long happens implicitly, but before this implicit conversion, an overflow occurs. Now to fix this, what we can do is we can cast one of these two operands to a type which is bigger than a signed int. So if we cast this 2 billion to a type long, then the result will be held in a variable. The result will be held in a data type that is the type of the largest of its operand. Now the two operands are, one is long, other is an int. So the result will also be a long, which can hold 4 billion. So after this modification, we should see that my real money should be 4 billion and there should be no overflows. Okay, so now we can see that my real money is 4 billion and there are no overflows. So the way we fixed was we used static underscore cast to change the type of this variable from an int to a long. Now we will see another way overflow can occur in C++. Here I'm declaring a variable called f. Its type is an unsigned int. It's initialized with value -3. We know that unsigned int can only hold positive numbers, and we're initializing it here with a negative number. So what happens is an overflow. So we will execute this line and see what will be the value of f after this assignment. So notice again, we are seeing a really big number, which means an overflow occurred, and now this is close to the maximum value an unsigned int can hold. So it's actually 2 to the power of 32 minus 1 minus 3 instead of -3. So again, pay attention, an implicit conversion can occur. So we need to see what is the data type that we are storing a variable as and what are we initializing it with. Next, we will see an example of a C style cast versus a C++ style cast. The first line is a C++ way of casting a variable. A cast here is informing the compiler that we want to explicitly change the type of a variable. Here we know that -3 is a signed literal, and we want to convert it to an unsigned integer. So to do that, we will use static underscore cast. The old way of doing this is by using a C style cast, which is more powerful, and therefore you should not be using it. So a C style cast begins with a parenthesis. Within parenthesis, we will write the data type that we want our variable to be converted to. So again, here we want -3 to be converted to unsigned int. We will go through different types of casts in C++ in a later video, and we will also see why C style cast should not be used, because it's too powerful. Unless you know what you're really doing, please don't use a C style cast. For your programs right now, a static cast will be more than sufficient. So whenever you want to change the type of a variable, use static underscore cast, and within static underscore cast, you mention the type of the data type that you want to change to. Okay, now let's see examples of using an unsigned long. Here I want to declare a variable called my_password and store a really big password within an unsigned long. So this is a 10-digit password. 123456789 is the number that I want to store within an unsigned long. We know unsigned long is 8 byte or 64-bit. So it can hold up to 2 to the power of 64 minus 1 within it. So we know that 123456789 is definitely less than 2 to the power of 64 minus 1. But notice before printing this variable, I'm actually using static cast to change the type of this variable from an unsigned long to a long. Now let's see whether what will be the output. If this number is less than 2 to the power of 63 minus 1, we should see the same number back. If it is greater, we will see an overflow. So let's continue the execution. And notice now my password is still 123456789 after using the static cast, which means it is less than 2 to the power of 63 minus 1. Now in the next line, I'm declaring a safer password, which is 20 digits. So I'm again using unsigned long to store this integer. And here I'm repeating the previous password twice. So it is 123456789 followed by 123456789. Now notice that this is still less than 2 to the power of 64 minus 1. So this is a valid assignment. However, is it still valid to use static underscore cast and change the type from an unsigned long to a long? The question is this less than 2 to the power of 63 minus 1? We will soon find this out by running the program. If it is less than 2 to the power of 63 minus 1, we should see the same number back. If it is greater, we should see an overflow. Okay, so notice that the result is a negative number, which means an overflow occurred. That is, my underscore safer password is too long to store within a signed long. And the lesson from this is that we should pay attention to what we are doing when we're using static cast. It's too powerful. So when the password was small, it was okay to change the type from an unsigned long to a long. But when the password was longer, it was not okay to change the type from an unsigned long to a long. Next, we will see a variant of an overflow. Here we are dividing 9 by 4. We know that 9 is not divisible by 4. So the result will have both integer and decimal part. However, since both the operands for this division are of type integer, the result will also be an integer, which means that we will see only the integral part of this division and we will not see the decimal part. So let's confirm that by executing the code. We see that 9 divided by 4 is equal to 2. So what happened here is not overflow, but this is truncation. So we know that the result will be correct if we cast one of this to a type float. But since both of them are of type integer, the result is also an integer. Now the last thing that I want to show you is what happens when we divide a number by 0. In C++, dividing anything by 0 causes an undefined behavior. Therefore, this piece of code is also commented. So what's important to know is that whenever you're doing division, make sure that you always check whether the value is greater than 0 and divide only when the value is greater than 0. So this concludes the module on integers. We began by looking at different ways of representing an integer in a C++ program. The three different ways were using the decimal or base 10 number system, using binary or base 2, and using hexadecimal or base 8. We saw situations where declaring a variable in base 10 is easy when the number is really small. And we also saw instances where declaring the variable in hexadecimal was easier when the number was too large. And we saw that binary representation was useful because when we want to represent negative numbers, we will use 2's complement representation. And to do 2's complement representation, we need first the 1's complement, which will flip values of the binary representation of a variable. We also looked at two special template functions, std bitset and std numeric underscore limits. And then we understood what are the different modifiers for an integer data type. The modifiers were signed, unsigned, short, and a long. And through examples, we saw when to use these three short, long, and a long within a C++ program. And we saw that if we are not careful as to what data type we will be assigning a value with, an overflow can occur. And it will be difficult to actually debug and find problems like overflow in a program. So it's very important to pay attention to the code that we are writing when we are writing and think about these issues and not debug it when your program becomes, let's say, like 1,000 lines. It becomes really hard to find out where the actual issue is. In the next video, we will start with a new module. We will look at floating point numbers within a C++ program. And we will also encounter similar issues like overflows within a floating point representation. So some of these would be similar to what we have seen in this class. Thank you so much.